E equals mc squared, the most famous equation in the world, describes the fact that anything with mass possesses a huge amount of energy, in principle. Like, a 5-kilogram cat has enough energy in its mass to power the entire country of Norway for a year, if only the energy could somehow be fully extracted from the cat. But it turns out that efficiently extracting energy from mass is a very hard thing to do. Antimatter is the most efficient way of extracting energy from mass, since if you collide a cat with a cat made of antimatter, 100% of the mass of the cat and anti-cat will be converted into energy, powering Norway for 2 years. But the universe has almost no naturally occurring antimatter, so it's not a practical choice for generating energy, since you'd first have to use a lot of energy to make a large mass of antimatter. Since we can't use antimatter, there are basically 3 options left to us: chemical reactions, nuclear reactions, and gravitational reactions, like matter falling into black holes. To start, chemical reactions are so bad at extracting energy from mass that we don't even think about what they're doing as converting mass to energy, even though it is. As an illustration, reacting a balloon of hydrogen and oxygen gases creates a nice big explosion, but the end products of the reaction only weigh half a nanogram less than the initial reactants, which amounts to a measly 0.000000001% efficiency of converting mass into energy. At that rate, you'd need 10 billion cats to power Norway for a year. Nuclear reactions are a lot more efficient, but still pretty mediocre on an absolute scale. Splitting uranium-235 into krypton and barium converts only about 0.08% of the uranium's mass into energy, and fusing hydrogen into helium, like in the sun, converts about 0.7% of the hydrogen's mass into energy. At that rate, you'd need 150 cats to power Norway for a year. This is where black holes come in. They're about as good as it gets in our universe for extracting energy from mass, which may sound weird because, as you've probably heard, nothing can escape black holes once inside. But the efficiency of black holes comes from what stuff does while falling towards them, before passing the no-turning-back point of the event horizon. Anything that falls in a gravitational field speeds up, gaining kinetic energy, and if it then crashes into something, it can convert that kinetic energy into heat. That heat can then radiate away as infrared radiation, slightly decreasing the mass of the object. For planets and stars, this conversion of mass into energy is pretty pathetic. An object falling to the surface of the Earth releases only about 1/billionth of its mass as energy. That's basically as bad as a chemical reaction, and explains why we don't think of falling to the ground as a way of converting mass into energy. It's a really bad way. But black holes have something special going for them. They are stupendously small. A black hole with the mass of the Earth would be about 2 centimeters across, providing way farther for an object to fall. And since gravity gets stronger and stronger the closer you are to an object, objects falling into black holes get accelerated to ridiculous speeds. Specifically, an object falling all the way to the event horizon of a black hole will have kinetic energy equivalent to roughly half of its E equals mc squared mass energy. However, if the object continues to fall into the black hole, all of that energy will be stuck inside the black hole. The way to actually convert mass into energy that goes out into the universe is to have the object slowly spiral into the black hole, crashing into other stuff on the way, heating up, radiating that energy away, thereby losing mass and speed, slowing down more, spiraling to a yet lower orbit, and so on, all the way down to the innermost possible orbit. And this is exactly what accretion disks around black holes do. So how good are they at converting mass to energy? Well, for a non-rotating black hole, the innermost possible circular orbit is actually 3 times farther out than the event horizon, and in order to spiral into that point, an object has to convert around 6% of its mass into energy radiated away to the outside universe. After that point, if it loses any more energy, it'll plunge down into the black hole, and no more energy can be extracted. But at this 6% mass to energy conversion rate, you'd only need to throw 17 cats into a black hole to power Norway for a year. Compared to the 0.000000001% efficiency of chemical reactions and the 0.1 to 0.7% efficiency of nuclear reactions, 6% for a non-rotating black hole may seem pretty good. But rotating black holes are even better because of how they bend space-time. They literally drag the things orbiting them along with them in the direction of their rotation, which means the innermost possible orbit can be much closer to the black hole. The details depend on how fast the black hole is rotating, but for a very quickly rotating black hole, the innermost possible orbit coincides with the event horizon, instead of being 3 times farther away. And the event horizon itself is half as big as for a non-rotating black hole. Combined together, this means that matter falling into rotating black holes can convert as much as 42% of its mass into energy. Or equivalently, you'd only need 2.5 in-spiraling cats to power Norway for a year. So if you really want to take advantage of E=mc² and convert the mass of an object into energy, don't bother with chemical reactions, or nuclear fission, or nuclear fusion. Just throw it into a black hole. If you're wondering how I calculated the efficiencies of converting mass to energy, you can just take the energy any reaction releases and divide it by the mass times c² of the things involved. For example, when radium radioactively decays into radon and helium, it releases 6.5 MeV of energy, and the mass energy of a single neutron or proton is about 940 MeV. So I'll leave it to you to figure out how efficient alpha decay is at converting mass to energy. Or you can learn more about nuclear fission and fusion by finishing this quiz on Brilliant.org, which is this video's sponsor and is full of interactive quizzes and mini courses on physics and math. If you really want to understand physics deeply, you have to work through calculations and solve problems yourself, and Brilliant offers an interactive online way to do just that. You can check out their course on black holes for free using the link in the description, and if you decide to sign up for premium access to all of their courses, you can get 20% off by going to brilliant.org/minutephysics. Again, that's brilliant.org/minutephysics, which lets Brilliant know you came from here.